and welcome to the MIT System Design and Management Program's Systems Thinking webinar series. Welcome to over 500 people from all around the world. We are very pleased to have you join us for Dr. Bruce Cameron's presentation today on system architecture, strategy, and product development for complex systems. Please note two quick items. One is that you'll receive a link to the slides and the recording later this week. And the other is there will be a Q&A after Dr. Cameron finishes his presentation. Please type your questions directly into the chat section addressed to all. And with that, I'll turn it over to Dr. Cameron.
Thanks, Lois. This is Bruce Cameron from MIT, and today we are very excited to be doing the virtual launch of our book, System Architecture, Strategy and Product Development for Complex Systems. This is the result of 20 years worth of work in the MIT System Architecture Lab, and we've devoted a lot of the last 4 years to bringing this book out to the market. Brief background on myself. I run the System Architecture Lab here at MIT. I teach in the Sloan School of Management as well as in the School of Engineering, and specifically I teach in the SDM program for our System Architecture course. I'm also the founder of a consulting firm called Technology Strategy Partners. Let me start by saying system architecture is as we have seen it, a very powerful idea. When we began to write this book, we observed that many of our coworkers, many of our students, many of our clients actually had a shared recognition of this idea and understanding of this idea. But at the same time, many of the people that we spoke to about this use this term in very different scopes and in very different contexts. So really what I'd like to explore with you today is what is the power of this idea, where is it used, and what are the analysis and methodologies that we've seen around this. I will say at the very outset, this is very much a science and an art. We, the authors, my co-authors Ed Crawley and Dan Selva, harbor no fantasies that this is a linear process, that this is prescriptive, that what I'm going to show you today is going to compute the answer for architecture. But I'm going to try and share with you what we've learned from our experience over the last 20 years in this field. So without further ado, I think we'll get started. So I'm showing on the screen a representation of Twitter's architecture. This was released by Twitter a couple of years ago. It's essentially a call diagram for the major modules of Twitter's architecture. And in the bottom left, you'll see what Twitter had captured about the performance of what they call their original architecture and then the resulting performance of a new architecture. This was a substantial effort that Twitter was pushing out. I don't know if any of you had experienced at some point challenges using Twitter, but for a time Twitter was the world's largest Ruby on Rails installation, and given their massive growth, had begun to see challenges to the scalability of that existing architecture. They re-engineered that architecture as represented here on the screen, and had achieved a reduction in response time for a number of their performance metrics. The reason I'm showing this to get us started is this was labeled as the architecture of Twitter, and the question that I wanted to start us off with is, how do we show architecture? As represented here on the bottom left, we would understand the term architecture to mean the old implementation and the new implementation of Twitter's back end, providing services to users. Is this the right representation? Is this the only representation? I want to contrast a number of different representations of architecture, and we'll try and tease out some of the differences that we see in the use of this term. So working from Twitter's architecture to an entirely different domain, the term architecture is used in the context of product design as well, for physical products. And here I'm showing a number of different full suspension mountain bikes. And the question that's being posed here is, how many different architectures do we have? Is a full suspension mountain bike an architecture for a bicycle? Or by contrast, would we say that there are a number of different architectures, perhaps not 9, but a number of different architectures shown on the slide here. So this term is often used comparatively, i.e. the architecture of this mountain bike is different from the architecture of that mountain bike, calling out certain features of, and again, we're sort of faced with the question here, is the architecture a subset of the design? Is it the entire design as realized and shown in the 9 pictures here? There's something in common between Twitter's use of the term architecture and the use of the term with respect to mountain bikes, but can a term that is used as broadly as this really have an internal meaning that can carry between these two very different domains? So I'm showing the first of a couple of definitions that I'd like to share with you over the course of the next hour. The first on the left-hand side is from the International Standards Organization, calling the architecture the fundamental organization of a system. And on the right-hand side, I'm showing a definition from the Open Group, which has published a number of architecture frameworks. And I've highlighted here a formal description of the system or a detailed plan of the system at a component level to guide its implementation. The question that I think this juxtaposition begs is how much detail is required in order to capture the architecture. And on the left-hand side, I'm showing a box diagram for the electrical architecture of a BMW. And on the right-hand side, I'm showing a CAD representation of that same electrical architecture. Is the full detail that's shown in the CAD required in order to understand the architecture? Do we have to see the finished vehicle in order to understand its architecture? Or by contrast, would we imagine that the box diagram on the left-hand side could in fact capture the relevant or powerful pieces of the architecture? One of the other definitions that's very prevalent when we went looking around in the writing of this book, we found a whole field that really thinks about architecture as form and function. There's a number of quotes that all of us know. Form follows function was a famous quote given. I want to just explore that in the context of the bridge that I'm showing on the screen here. If we think about the function of the bridge from an external function perspective, transporting people from one side of this river to the other side, we could also think about internal functions of the bridge, carrying load, transmitting load, and so on. We could talk about the form of the bridge, namely that there's a roadbed, there are a number of cables, there are 2 central towers. What does this description of the form and of the function tell us about this bridge? Well, if we contrast 2 bridges, we might be able to pull out some of the relevant details of the architecture here. To first order the form of these two bridges is very similar. On the bottom right, the same that I had showed on the last diagram, showing the top left bridge, we again have two towers covering the span. We have a number of cables, we have a roadbed, and yet we label these two bridges with different names. How are they different, and does that relate to the architecture? Well, looking at them in more detail, what we would understand is that suspension bridge supports the main span using vertical cables, that is the form. If we look at the cable stay bridge, the cables are actually diagonal, and if we were to look into the function here, we would see that that in cable stay bridge, the roadbed actually carries load in compression created by those cables. There are limits to cable stay bridges. There are advantages to cable stay bridges. The advantages are that you require a substantially smaller anchor point to land on both ends, and that the physical structure of the bridge appears lighter, or the roadway looks smaller in comparison to the truss structure found beneath the roadbed of the suspension bridge. However, there are limits that given that the roadbed is taking load in compression, it's subject to buckling, and there's only so great a span that can be spanned by a cable stay bridge. By contrast, in a suspension bridge, we can span a much greater body of water, and yet we require substantially larger anchors on both sides in order to hold tension from the main cables. So we have names for these different bridges. At first glance, you may not have known those names. We have similarity in form, and we actually have similarity in function. What this example starts to demonstrate is that the mapping of that form to function, namely whether the roadbed here carries load and compression or not, helps tell us something about the architectural differences between these two bridges. We do not necessarily need to know everything about the bridges in order to understand these architectural differences. So form and function can be a guide, and really the mapping of the functions to the form is another possible concept of architecture that I'll continue with here. I've pulled two more definitions here. Overk and Eppinger is a famous product development text, the arrangement of functional elements into physical blocks. And then I've quoted another text here, the whole consists of parts. The parts are relationships to each other, which when put together, the whole has a designed purpose and fills a need. So I'm calling out some of the pieces and trying to build our definition of architecture. We have form and function, we have parts and whole, we have relationships among those, and at the end of the day, from an architectural perspective, we expect to see some emergence. We expect to see this as a system that the sum of the elements is somehow greater than those elements individually. So to illustrate this form to function mapping, I'm going to show a brief example here. One of the things that we observe in the book is that many types of transportation systems have fundamentally the same three internal processes or functions that at some level they all provide lifting or supporting function, that they all have a propulsion function, and that there's always a guiding function at some level. There are a number of different forms that we can use to accomplish those functions, and as we sort of mix and match the forms to those three functions, we get different systems out. So if I used wheels for lifting, propelling, and guiding, I would have a car. By contrast, if I used wings for lifting, a jet for propelling, and a rudder for guiding, I would have a jet aircraft. If I enumerate all of the possible different combinations here, one of the powerful pieces of system architecture as a discipline is the idea that we can begin to enumerate new architectures. We can mix and match and try to understand, are there other architectures out there? And just for interest, I've done that with a number of other feasible combinations of those instruments and internal processes, and we see a variety of different types of transportation systems, ranging from a helicopter to a jet boat. So that enumeration is powerful here. Where I'd like to take the idea is what are the feasible combinations, because clearly not all combinations here are possible. How do we understand this mapping? In this next example, I've essentially done the same thing by representing functions that a home networking, how you connect to the internet at home in order to send a message, by illustrating some of the core functions, a number of the possible forms that I can use to accomplish those, and then trying to represent the combinations of those form and functions. Here on the slide, what I'm showing is a representation of a network, one possible network that would emerge from that. But here I'm trying to explicitly illustrate, how do we map these forms to functions? Which ones are tagged to which ones? I'm showing the physical layer on the right-hand side and the link layer in the middle. I have a number of circles which are representing the functions, and boxes which are showing operands and instruments, two of the terms that we use in the book to begin to sort of tease apart the form and function idea. But I think the real power of diagrams like these that we've tried to illustrate in the book is trying to build an understanding of how is form mapped to function, where is form mapped to function, and what does that tell us about the architecture. Could I take, for example, this diagram, which arguably is pretty complex and not easily readable? Could I predict something about the behavior of the system from just this form to function mapping, or would I have to layer on other dimensions? So one of the ways that that I found to try and illustrate this this question is to simplify up a level and to really ask, what are the decisions that we make when we generate architecture? Can we call these key architectural decisions out in order to illustrate the main differences between them, rather than going through the complexity of that form and function mapping? So what I'm showing here are two military aircraft, just for comparison. On the left, I have traditional tube and wing aircraft with engines shown below the wing, and on the right-hand side, I'm showing a stealth bomber, which is a configuration called a flying wing. You'll notice it has no vertical tail, nor does it has what you might call an integrated fuselage. The whole body of the flying wing is a lifting surface. So what are the key architectural features that separate these two designs? Well, we could call a number of them off, namely, on the right-hand side, the engines are integrated into the fuselage. On the left-hand side, they're more modular and slung below the wing. We could call out that there's a tail on the left-hand side and no discernible separate tail present on the right. We could show that the back edge of the flying wing is serrated, that there are control surfaces pointing at 90 degrees to each other, which is different from the alignment of control surfaces on the left-hand side. And how many of these differences would I have to illustrate in order to argue that these are different architectures for these two planes? So we could go through a number of them. I want to actually take this even a step further and ask, we made decisions as to whether we were going to choose a flying wing or a tube and wing aircraft. What now happens if we decide to build a family of those aircraft, as is very common in both the civil and the military aerospace environment? So now I'm showing two civilian examples. On the left-hand side, a family of A350s that you'll notice differ primarily in length. And on the right-hand side, a proposed Boeing design of a family of flying wing aircraft, but for civilian transport. If we ask the same set of questions, what are the architectural features that really separate these two, we start to see some important implications for the family here. So what is that implication? Well, it is when I design a tube and wing aircraft for a family, all else being equal, I have to design, generally I keep the wings common across, in this case, the A350 family, and therefore for the wings I have to design the lift produced by those wings to support the heaviest possible aircraft I could design to attach to those wings. Which means that if, in effect, those wings are over-designed or oversized for the two smaller aircraft, and that I encounter performance compromises as a result of that, whether they be in fuel burn or in range or otherwise. On the right-hand side, what's interesting is the concept of the family suggests that I cut the aircraft in half and I add center sections in, and when I do so, what we notice is that I'm not only adding weight to the aircraft, but I'm actually also adding lifting surface. There's a synergy here that, in essence, the outboard wings do not have to be as over-designed for the heaviest aircraft because they scale, the lifting surface scales with the size of what's called here the blended wing body aircraft. So, you know, I made these set of early architectural decisions, I'm arguing, as to whether do I have a tail, whether do I have separate wings and fuselage, or do I integrate them. And then, you know, I have some set of consequences that are incurred downstream in manufacturing, but also from a product family perspective here as I think about subsequent designs. And the real question to the architect is, how do I pull these downstream considerations, like how will it be manufactured and like will we design a family of aircraft, how do I pull those up front into the architecture process and understand, is this an important architectural feature that we need to engineer in? Is this a feature that we can save for downstream design? How do we pull those out? Can we pull those out? Is really the question that's being posed here. So this framing as decisions we find is very powerful because it's a condensed representation of architecture, and it allows us to, in a sense, trade what is an architecture at a very early stage. We don't necessarily have to design the whole system in order to understand what is its performance. We can represent it as decisions, do analysis on those decisions, and then try to understand early how those decisions interact or are synergistic. One of the portions of the book that we spent a fair bit of time writing on was, you know, how do we think about architecture as decision support? Here I'm capturing a distinction by Herb Simon on program versus non-program decisions. You know, in essence, program decisions are well-defined, can be modeled and optimized. I'm showing a number of examples lower down. What's the best market strategy for our established products? Given that we know which office supplies are available, which office supplies should we order for our needs? And on the other end of the spectrum, I'm showing what we're calling sort of non-program decisions, which are not routine decisions and don't lend themselves as easily to what we traditionally think of as decision support or optimization. And the latter is really where we believe decisions in system architecting fall. And the endeavor that we had for this book was simply because these decisions are non-routine doesn't mean we can't capture them. How do we work to capture them? In what areas can we capture them? And in what areas does this remain a human decision process, a management decision process? So we introduced the framing of architectural decisions, and I love this quote from Daniel Kahneman, the Nobel Prize-winning psychologist. We have no reason to expect the quality of intuition to improve with the importance of the problem. Was certainly a lesson that I learned in my personal experience, and the question becomes, what support can we bring to that? So we framed here architectural decisions as a subset of the design decisions and those that are most impactful. I already spoke about the form to function mapping. We'd expect there to be important decisions as to how do we map form to function. These decisions determine the performance envelope. They encode the key trade-offs somehow. And at the end of the day, we would expect that making one choice on an architectural decision versus making another should lead us to architecture and products that are fundamentally different from each other. So whether I choose to power the front wheels or the rear wheels of a car, I would expect a very different layout of the vehicle. I would expect a very different performance trade-off to be taking place. How do these architectural decisions help us, help us in the process of developing a product or system? Well, we advanced two sort of tests for architectural decisions. The first is, does this decision have a strong influence on its metrics? Is it, in a sense, do we see sensitivity? If I choose a front-wheel drive layout for my car, do I see substantially different fuel economy? Do I see substantially different structural weight for the vehicle? By contrast, there's a connectivity element here. So if I make this architectural decision and then I want to change it later on, do we expect there to be substantial rework to change it? Is this a decision that I can make downstream with regard for other decisions? So thinking again about a car, the choice of cloth versus leather seats is not an architectural decision. There is an impact on a metric, cost, that leather seats are more expensive. However, regardless of whether I choose a front-wheel drive or rear-wheel drive or an all-wheel drive architecture for the vehicle, I can make that cloth versus leather seats decision far downstream in the design. It is not tightly coupled. And we believe that architectural decisions do display this connectivity or this coupling. So I'm going to walk through an example to try and illustrate these two and talk about architectural decisions in the context of the Apollo program. So this, I think, is arguably before the advent of system architecture as a discipline, as a field, as a term that people used. And I want to ask, what are the differences in the possible architectures that were available? Can we characterize the architecture of Apollo? This was some work that we did here at MIT. We looked at 9 possible architectural decisions for, in essence, going to the moon, and we asked the question, could we replicate the Apollo decision as a historical case study? There's a number of decisions that were clear to the folks making these decisions at the time. Notably, when I first launch into Earth orbit, do I pause and rendezvous with another spacecraft called Earth Orbit Rendezvous? When I go to the moon, do I descend directly onto the lunar surface or do I go into lunar orbit? While I'm in lunar orbit, if I'm in lunar orbit, do I have any rendezvous that require me to meet up with another portion of my spacecraft? And so on. So those decisions are listed here, and I want to explore what are the connectivity, what is the sensitivity and the coupling between them. I've shown here a picture of John Houbolt, who is known as the father of the architecture for Apollo. He was an engineer working for NASA who had advocated this lunar orbit rendezvous approach of separating the spacecraft into a module that would stay in lunar orbit and a separate module that would go down to the surface. What's interesting when you look at the history of this program is that there was 2 years in which, largely prior to Kennedy's announcement, NASA churned on possible architectures, possible decisions about going to the moon. There was an enormous amount of design work that took place, but there wasn't necessarily a speed of progress in those 2 years. And that when you look at there was a decision process to choose lunar orbit rendezvous, even though it is a risky idea to try and meet up and then mate 2 spacecraft in orbit around the moon, there were a number of fuel advantages and other advantages that happened from that. Once this decision took place, the architecture sort of unfolded, that the design process really accelerated. The rate at which the engineers were able to build technical detail into the design really accelerated. So this was very much a sort of crux point for the program, the making of this decision. When we go back and historically analyze this, what was interesting to us was we enumerated many different possibilities, many different combinations of those potential decisions, like do we meet up in Earth orbit, do we meet up in lunar orbit, and then we ranked them on two axes here. One, initial mass in low Earth orbit, which is called MLEO on the left-hand side, essentially how much mass you have to put into orbit. And the second on mission success probability, or you can see that as riskiness, with the utopia point being in the bottom right here. And what's interesting about the exercise was that we found there were essentially three main architectures that really dominate this space. There are architectures that involved what Wernher von Braun had proposed, a direct mission. In the monopoly sense, this is do not stop, continue past go, collect your $200, and proceed further along the board. This was go directly to the lunar surface, do not stop in lunar orbit on your way. And those have, in fact, a maximum success probability, but are also the heaviest architectures. We see a whole bunch of architectures that are really Apollo-like, that involve lunar orbit rendezvous, and then we see a number of architectures like the ones that were considered by the Soviets at the time. Minimum mass, minimum crew, one crew to the surface instead of two, as was used by the Apollo program. It's interesting that this result was not baked into the analysis that we ran, but somehow three dominant architectures arose, which happened to be the three dominant architectures at play in the 1960s when this space race was going on. So I mentioned earlier that there are sensitivity and connectivity when we look at architectural decisions. What I'm showing here is a representation we have in the book about how do we make architectural decisions? In what order should we make architectural decisions? And what I'm arguing is that decisions that are both sensitive, i.e. On which our metrics depend, and decisions that are strongly connected to other decisions should be made first before decisions that are sensitive, i.e. have a big impact on our metrics but are weakly connected to others, and that overall we should save those decisions that are insensitive and weakly connected till last, like the cloth versus leather example that I gave. So what does this tell us about how we might have sequenced the set of architectural decisions for Apollo? So if I use a model and I plot degree of connectivity and the sensitivity of those of the two main metrics, what we came out with was a possible organization of architectural decisions. So what's interesting is this choice of do we do a lunar orbit rendezvous or not percolates to the top as a very connected and very sensitive decision. We then have three other decisions, sort of decision pairs that are made. Do we depart directly from the moon, from the lunar surface, and do we arrive directly to the lunar surface, or do we not? And as well as crew and fuel choices that we make for the different vehicles. So this is a representation of possible sequence for the decisions of the program. The question that we're sort of asking with this historical case study is, if we had the ability to look at these decisions, to compare their combinations, and to produce this summary, would we have structured the program differently? Would this list of decisions tell us which problems to tackle first and which problems to tackle later on? So this really, I think, gives rise to the opportunity that's presented from system architecture, which is you know, that today we, you know, we build complex and increasingly unprecedented systems. There's very active questions when we do so. You know, will they meet stakeholder needs? Will they evolve with time, or will they die as with past architectures and past designs? And what we assert is that well-architected systems do. Well-architected systems give the design program a fighting chance to succeed with the design, to succeed in the market, and really to generate competitive advantage. Decisions taken early in the program do not ensure its long-term success, but they can certainly handicap its success. You get the architectural decisions for a program wrong, and we've seen a number of past case studies that are written up in the book where the program never really had a fighting chance, that they didn't manage to make use of the synergies available, of the real leverage points of the architecture. On the right-hand side, I'm showing two examples that I've been fortunate to be involved in, and we had contributors help us with in the book. On the top right, Dr. Carlos Gorbea contributed from BMW some excellent work on the comparison of different architectures for a hybrid vehicle that was at the heart of BMW's decision to pursue the I sub-brand. And on the bottom right, I'm showing an oil platform, which is an example of a system that we had studied from an architecture perspective to try and understand what are the key architectural decisions, particularly in icebound environments. Would you design an oil platform differently in an icebound environment, and is that somehow core to its design? So as we think about architecture, one of the other sort of features of architecture that comes up frequently is how complex is the architecture? How complicated is our representation? I'm showing nobody's dream of a server room here, what I'm calling a complicated network. And you know, just visually, it's you know, it's hard to understand what's going on here because there's so much going on. This is certainly complex, but it's also complicated in a sense that it's not easily understood. It may be a very high-performing server room or architecture, but how complicated do we need to make it? Is there an opportunity to simplify that representation? So we talk in the book about apparent complexity or how complicated a system is. Complicated systems are hard for people to understand. Now, you know, complex systems involve you know, functionality that is difficult to deliver, but we actually try and separate these two. That we believe one of the roles of the architect is to reduce the complicatedness of the system representations, that the architect is there to invest in complexity, obviously, to develop new features and functionality, but to explain those to members of the rest of the corporation, to users, to the manufacturing environment in a way that tries to reduce how complicated it looks. So if I contrast that against another server room where I have tightly bundled cables, we might imagine that performing changes on this second server room would be easier. That it would be also easier for people to understand how to put a new one together. So is this sort of graphical representation that I'm showing, is this real? Is this something that we can implement? By contrast, I'm showing here a picture of the cockpit of the Concorde, and the number of dials and switches in this cockpit is enormously complex. Question is it complicated? Did I need all of this complexity in order to deliver the astounding performance that the Concorde offered? Now, there's a whole set of user interface design questions here, but I'm really just using this as a metaphor to ask how much of this complexity that's inherent here was really required to deliver the functionality that the Concorde delivered. And one of the things that we've come to observe about architecture is good architecture helps make complex things, complex endeavors, less complicated. And they do that partially through the form and function lens that I illustrated. There's very much a question of how do we represent entities and their relationships. And there's really a question of emergence here. Can we simulate, can we predict something about architecture and the performance of a system from a set of early decisions? What is our ability to understand downstream how this architecture will perform? Is there an opportunity to trade early? We found a number of systems in which there was, and this is really the sort of at the core of the book. I want to speak briefly about the role of the architect. I love this quote from Abraham Lincoln. Some single mind must master, else there will be no agreement in anything. The role of the architect, there are 4 parts in our new book, and we devote an entire part here to how do we manage the architecture process? How do we understand roles and responsibilities as viewed through the lens of architecture? What does this suggest about, among other things, how we make corporate strategy decisions with respect to the architecture if we're expecting that our architecture is going to give us competitive advantage in the market? We call out 3 key roles of the architect in the book. One of the most prominent early on being, the architect reduces ambiguity for the design team by interpreting, working with, and setting bounds around corporate strategy decisions and technology insertion decisions. Downstream of that, the architect is a central player in encouraging creativity and in guiding the team as to how broad a set of solutions to seek. And then I think one of the real pivotal roles for many of the well-known architects that we've had the privilege of working with that really distinguish them is their ability to manage the complexity of the architecture downstream, to produce representations, to articulate decisions so that people can contribute different pieces to the architecture without sort of losing sight of what the total purpose of the architecture is. And I'm showing on the slide here a substantial corporate decision that BMW took to exit F1 as they perceived macroeconomic trends really in favor of entering the BMW, what became the BMW I brand, fuel-efficient set of vehicles, the i3 for city driving, the i8 as a representation of what a sports car could be that was not compromising performance and yet was delivering substantially better fuel economy. And then on the bottom graphic there, this resulted in an enormous investment in carbon fiber for BMW. How did those downstream implications of manufacturing carbon fiber at scale, how are those represented early on in the choice of this architecture? How did they get pulled back upstream to understand where they were going to trade off against other corporate strategy decisions? This is really one of the key roles of the architect in our opinion. So I'm going to conclude with a couple of points on patterns and styles. Because one of the things that when we were looking at writing this book, people asked us was, what are the patterns for good architecture? What patterns do they display, or is there a style of architecture that's been more successful in the market than other markets? I'm going to illustrate these with Earth observation example. This is a number of satellites that NASA was at a time proposing, some of which have been implemented and others not, to survey the atmosphere and the surface of the Earth. What can we learn about patterns and styles of architecture from this? One of the patterns that we observe is, architecture problems often take the form of trying to subdivide a number of known elements. So if I had, in this case, 6 instruments that I wanted to put on orbit, how do I choose how many satellites I put them up with? Do I put them up with 3? Do I put them up with 4? And then if I choose 3, how do I sub-segregate the instruments into satellites? So we call this the partitioning pattern, and in the book we actually introduce this as one of the what we believe are 6 canonical patterns in architecture. One of the things that comes up in the partitioning pattern is what we've called the style here. And I'm calling it here monolithic style versus the fully distributed style. Thinking about those instruments that I showed on the previous chart, we could think about putting them all on one spacecraft, and there'd be a number of advantages that we'd be taking measurements at exactly the same time and from the same location. However, I'd be producing an enormously complex and potentially complicated spacecraft, versus I could think on the other end of the spectrum, putting all of those instruments on individual satellites. There's a set of synergies and a set of repulsive forces or interferences that take place there. This is one of the tensions in architecture that we call out as a style. And one of the things that we observe is great architects have the ability to understand what are the central tensions in architecture and to call them out, represent them for decision making. On the next slide here, I have illustrated a number of other what we've called patterns. We believe there are at least 6 patterns that take place in sort of architectural decision making. Decision option I had really spoken to from the Apollo example, that we have a set of decisions like, do we rendezvous in lunar orbit, yes or no? And then I showed the partitioning example as, given a set of elements, how do I subdivide them? And the example given, how do I put them on different spacecraft? How many spacecraft do I put them on? These decisions, we see a number of different ways to represent these decisions, and the sort of last portion of the book is really devoted to exploring what are the areas in which these types of decisions are well encoded for decision support, where we can expect some science from system architecture that we could run a model and try to understand how the decisions can be sequenced. And where's the boundary with the art of system architecture, where decisions are not easily set up along these lines, and what guidance do we offer? The book has a number of case studies that talk through past system architectures from the perspective of the architect, where we try and call out where's the science and where is the art in this. So I want to leave you with 3 thoughts here from this talk. The first is that architecture can be an explicit choice. It is not always, and we really, I think, prefer to succeed by design rather than from luck. For many complex systems, there's this idea that we can't control the complex system, and I think this book is really a counter to that. What are the opportunities to frame architecture as a choice? And then if we do so, how do we make architectural decisions early? How can we sequence them? How can we think about them, regardless of whether I develop a model to support that activity? The decision representation from a management perspective is a very powerful one. And then the final thought I wanted to leave you with was, the system architect is really charged with making complex systems less complicated. And that, in my experience, and I've had the good fortune to work with a number of architects over the course of my career and over the course of writing this book, the great ones are really called out as an explicit role and see themselves in a position to manage the complexity of the representations and to manage the architecture of a process, not leaving it to chance. So I'm going to conclude with that. I'd like to thank many of the people who made this this book for us a reality. I have the good fortune to have a number of them with us today on the call, and for those of you that are interested, we have a number of contributors to the book, where you can read more about it. But I'd really just like to take the opportunity to thank all of the people who helped make this a reality for us. So I'll stop there and invite questions that have been gradually accruing in the chat window here.
Okay, Bruce, excellent presentation, says Mark Simon, and folks are also commenting on your book. However, the chat questions are really more of a discussion. I have copied them and sent them to you by email. Wonderful discussions from Keith Chamberlain and Steve Spear and a number of other folks, but I'm not quite sure how to go about doing a Q&A here, since much of this is much of what people have entered are comments. So if anybody has any questions or comments, please enter them into the chat section while Bruce is able to scan what I've sent him, and then we can proceed from there. When you enter your question, please address it to everyone. And here's a question that was a source of much discussion. How is architecture fundamentally different than engineering?
And that's a question that we got all the time in the class that I teach here at MIT on architecture. I think that I dispute the premise of the question in the sense that I believe that architecture is a part of engineering. It doesn't have to be fundamentally different from, but doing architecture right means broadening its scope beyond engineering in some considerations as well. That if we treat architecture as only a technical endeavor set by some inputs from the marketing team, that we're really at risk of missing out on the opportunity to engage with early customers, to engage with thought leaders in marketing and in corporate strategy, to work together to understand what the opportunity is from an architecture perspective, and also what are the constraints that the architecture is going to impose on our ability to go to market, on our ability to generate a product line from a given architecture. So I don't think the two are fundamentally different or separate. I think there is a big separation between architectural decisions and design decisions. Architectural decisions are made early, are very sensitive to the metrics, and are very connected to the rest of the design, whereas design decisions in many places are less connected and less sensitive. But I think it's really, it has to be a part of engineering, and it also has to be a broader set of considerations as well.
Great, thank you. From Julian Johnson, who asks, are you aware of quality function deployment, otherwise known as QFD?
Yes, absolutely, and this is mentioned in the book. QFD has really, I would say, taken off in the last 25 years, starting from some early days here at MIT. One of the central premises of QFD is that we can map, between the features of the system. And I think that's a powerful idea that's sort of tagged in the book for where it applies, but just also the broader idea that that architecture is a mapping between form and function, I think draws on some of the early work that was done in QFD and aspires to build on it.
Great. From Jean, who asks, how does your book address software architecture?
That's an excellent question. One of the I think opportunities that we saw, and also one of the great challenges of writing this book is, could we say anything meaningful that would be really worth people's time for a concept that is used so broadly across different disciplines? When we talk about architecture, there's actually more people with the title software architect than I think there are with the title system architect when we did the analysis for the book. So we believe there are shared sort of concepts between hardware and software. The book is our attempt to bridge those and understand what is underlying in common. But by doing so and working in that general environment, we necessarily have to leave behind some discussions from concepts in software architecture that really didn't carry over into hardware, and also vice versa. So what was sort of interesting to me in the process was there were a number of the early ideas that we had about managing decomposition as a choice and abstraction as a choice, which are actually much more prevalent in software architecture and a lot less prevalent in hardware. So the book was shaped to try and communicate that as best we could. But I welcome your feedback on the product is sort of completed now. Did it meet needs? I'd welcome your thoughts on the software architecture content that is in the book.
Great. Bruce, the questions are pouring in here. Let's see. What is, this comes from Guillaume Dupriez. What is the method you recommend for defining an architecture? Is SADT the best one? And where do you stop?
That's a great question, and I think one that we were trying to ask early on in the presentation. How much do we need to represent an architecture? Is the architecture, does it have to be the whole of the system, the product or the system as it is seen in completion, or can it be some sort of lighter or sort of abstracted representation of that? I think the book is really an attempt to try and call out what are the underlying principles that work in a number of different methods. So SADT, or structured analysis and design technique, is one of many out there. If I'm remembering right, this is something that led into the IDEF0 exercise, another sort of representation architecture that's very much tied to the TOGAF definition that I showed later on. Our interest was not so much in promoting a particular representation, because they have different strengths and weaknesses in a sense, but in trying to communicate what we've learned about when you would choose which ones, and in what scenarios which representations are more powerful than others. I'm happy to take the question offline, but it's a very valid one. Where does architecture stop, and can we determine, did we get the right architecture before we finish the product design?
Great. And speaking of taking the question offline, there are many questions still unanswered from the chat question. I want you folks to know that there will be, in addition to an email including the link to the webinar recording and the presentation slides, there will be Dr. Cameron's email address too. So if he doesn't get to your question in the next few minutes, please feel free to contact him by email. That will all be sent to you by the end of the week. The next question is from Carlos Morales. What are some meaningful metrics to evaluate a candidate system architecture?
That's a wonderful question. Carlos is a good friend of mine chiming in here. The discussion of how do we measure system architecture is I think an important one, and it's also a pretty nebulous one. When we started this activity, one of the things we observed is that the idea of architecture has some pretty nebulous boundaries. Nebulous boundaries make it hard to do measurement. So one of the ways that we we thought about this in the book are what are the possible sort of categorizations of measurement. You know, for example, in the Apollo example, I showed two. You know, one being risk as a measurement of the architecture, and another one being the mass launched to low Earth orbit. Later on in the book, we give some guidance about, you know, how can you put the architecture and your metrics in a loop to understand, you know, which of your metrics really help you differentiate between architectures versus which metrics, you know, when you evaluate them, don't give you any differentiation. And so we wrote that into the content of the book. I think I'd be remiss to say that there was anything sort of central across architectures that I can say any architecture should. You know, beyond I think the really broad suppositions of architecture should be elegant in some manner. Architecture should evolve easily. Architecture should be easily manufactured. You know, this idea of DFX, design for X, where X can be manufacturing, supply chain, safety, etc. There's a whole field that thinks through a number of different dimensions on which you could think about design. I think that really all applies here to architecture as well, but at the end of the day, we have to ask the question, which of these metrics help us differentiate between possible architectures, and so can help us make an architectural decision early on?
Great. Thank you. Bruce, will you have about 5 more minutes?
I'm happy to stay on for questions as they arise here. So
okay, great. Well, we ourselves have about 5 minutes left for this series. Again, folks, you'll be able to contact Bruce through the email address that we provide if your question doesn't get answered today. This is from Rodrigo. Does your book connect system architecture with system dynamics?
That's a great question. I actually, when I worked for NASA many years ago, system dynamics was actually the modeling tool that we were using at the time to forecast the budget for the program as well as its likelihood of technical completion. We actually don't spend much time in the book on system dynamics, not for lack of interest or experience. I think that the two are very complementary, and we have some diagrams in the book that, from my experience, are I guess just percolate in, you know, based on system dynamics and the associated sort of systems thinking and thinking about systems as feedback. But it's not something that we actively incorporated, nor is it something that we've spent that we've actually spent some time modeling. So it's certainly an opportunity from my perspective. You know, system dynamics has definitely answered questions in the field as to, you know, what gives rise to competitive advantage, and you can think about, you know, how does having a strong architecture, whatever that means, enable market success. You could think about modeling that from a system dynamics perspective, certainly, but not something we explicitly cover in the book this time.
Okay. I have another question about the book. This is from Jason Silbeck. Does the book cover what architects need in the absence of any data or precedent? In other words, how do you make good architecture choices about a novel design or a new market?
Yeah, it's certainly a challenge. You know, I could call that architecting in a vacuum if I wanted to be facetious about it. One of the things we didn't spend time talking about, which I am sharing on the slide here, is the idea of emergence that we cover in the book, but I think is a much broader idea about, you know, how is the sum greater than the parts. You know, thinking about how do you predict emergence is really the question you're asking. How do I predict it, especially in a vacuum where we have unprecedented systems? And really the 3 ways that we talk about are, you know, either we have precedent available, we have some ability to experiment with the system, or we have some either physics-based or other dynamics that we can model. You know, in the absence of that, I think is the real art of system architecture. How do you reason through. One of the great examples from my career, I was fortunate to meet Joe Gavin, who was the system architect for the lunar excursion module, the LEM that went down to the lunar surface. Joe talked about there was enormous uncertainty in the depth of the lunar regolith. We didn't know if it was a couple millimeters or if it was 3 meters that we were going to sink into. So we engineered all of this travel into the suspension because we had no idea how the surface would in a sense react. We got some sense of that when we started to send probes, but there was a lot of uncertainty in that process. I want to be true to your question and try not to give canned guidance about this, but I think thinking about the architecture phase as an explicit sort of feedback process where we're going to test out some concepts, we're going to do experimentation and modeling if possible, is a helpful one rather than the sort of traditional product development process idea where we presume linearity, we presume that we make decisions, we carry those decisions forward, we do not revisit them, we work towards increasing system definition. In very uncertain environments, it's often helpful, in our experience, to spend some time thinking about what does the architecture of the system look like, what are many possible architectures, and then to work from there.
Great. From Matt Alexander, what do you think of using patterns that span different industries? Are there any tips or best practices you see?
That's a good question. This idea of patterns is a very powerful idea, but it's also a challenging idea in that we think as framed the patterns are very broad, so by their nature would sort of span different industries. But we haven't done any against the patterns. We haven't tried to match them up to up against industries in the sense of which patterns recur more often in different industries. I think that's definitely I'm just thinking about it on the fly. Achievable work. A lot of the time that we spent was sort of how can we use novel machine learning tools? How can we use existing algorithms to develop to try and solve the types of program decisions or problems that could supplement the wisdom of the architect and therefore allow them to focus on the more sort of not programmed content or diffuse problems that need more human reasoning because we don't have the same tools to tackle them. But I haven't actually spent some time thinking about it. In case you can't tell, I'm an aerospace engineer by training. I've been fortunate to work in a number of different markets over the course of my career, from finance to NASA to heavy equipment and automotive. But I haven't actually spent time thinking about which patterns would apply more in which industries. So with your permission, I'll take that question offline and spend some time thinking about it.
Great. The last question that we have time for today, and I apologize we don't have more time, is from Telakapali Murthy, who asks, what matters most for executives or decision makers? How architecture helps decision making, especially the cost, and how can architecture help decision making, especially the cost in many cases? It's a little rough there.
Yeah, Telakapali, I'm sure I'm butchering your name, but I appreciate the question. I think it's a premise of the book. I think it's something difficult to prove. So we assert it in the book, and I say this in chapter 1, that system architecture, the idea of system architecture is really an assertion. Can we prove that there's leverage early in the design process? I think we could. Can we prove the counterfactual, that if we didn't undertake a system architecture process or an executive decision consultation process or a corporate strategy plus architecture process early on, that we would have achieved a different result in the market? Often difficult to determine the counterfactual. You're really into case studies at that stage. But I think the real premise of the book is that there is some subset of these decisions that you need to surface, and that really, you know, I love this saying, decision makers make decisions. You know, the question is, you know, how does the architect surface those decisions for executive consideration? Something we spent a lot of time thinking about in the book, but at the end of the day, difficult to prove its impact. So I think, you know, our attempt was really to write down what we knew and to use that as an engagement point to see what other people thought and what their experience was with executive decision making around architecture.
Great. Bruce, thank you on behalf of MIT and SDM for a fantastic presentation. Thank you all for your questions and your discussion points. I just would like to remind you that we will be sending out an email with Dr. Cameron's email address, slides, and a recording of this presentation. We'll also include info on our next webinar, which is May 18th, and will be delivered by Professor Dick Larson. It's on how to plan for workplace disruption in the presence of the flu. So those of you who are interested and also would like to plan now for any contingencies needed in the fall, please join us. Again, thank you, Bruce. Thank you, everyone, for your questions and participation, and have a great rest of the day.